So this vapor pressure calculation, this was probably, I don't know if it was the first, but it was the one I remember the most, calculation that I had to do in industry that required PChem. So when I got out and got into the quote real world, and they were wanting me to show that people working on the assembly line wouldn't be overcome by the solvent in a particular process that they used. And so I had to actually calculate what would the maximum vapor pressure be in that room if this solvent came to equilibrium with its vapor in the room. And so I had to use this equation to figure out what the vapor pressure was. And so let's jump into this. How would you calculate that? You know you've got a solvent, you know the lid is open, and it's going to be evaporating. What's the maximum pressure it would have in the room at room temperature? And so y'all are doing this in the lab this week with the van der Waals equation of state. And you have this correction, this equation that corrects for the attractions and repulsions of the molecules. So the A term takes into account the attractive forces, and the B term takes into account the repulsive forces. So think about this. If we talk about the ideal gas law, so let's just write it up here, nRT over V. If we have attractive forces, the pressure is going to go down because the molecules are attracted to themselves and they're not hitting the pressure gauge as hard. So there's less force on the walls. So that's this A term. You see, it's a subtractive term from the pressure. So that reduces the pressure because of the attractions of the molecules. Now, what about the repulsions of the molecules? When you think about the volume in the room, if the molecules take up space and they bump into each other, the space that they take up could account for the repulsions. And so we would subtract this piece based on this B term from the volume. It's like the room, and the room's volume's reduced a little bit, and it's a function of the number of moles of molecules. Because you've doubled the number of moles, you double the volume that the molecules take up. So this reduces that volume and actually raises the pressure. So these two terms help correct for non-ideal behavior. And so I've got the plot here in reduced variables. We talked about those last time. So this is the volume divided by the critical volume and the pressure divided by the critical pressure. And these are at various unitless temperatures. So that's temperature over the critical temperature. So when the temperature is at the critical temperature, we have this curve here. You see, this is above this number. These are all gases. There's no condensation available. Below that number, then you have condensation. So you have this region here that we saw last time on the PV phase diagram of the condensation region. Liquid and vapor in equilibrium. But the van der Waals equation does something really strange in that it's not realistic. Let's think about this. If I'm pushing on the gas, the pressure goes up. That makes sense, right? You push on a gas, pressure goes up. Look what happens with the van der Waals equation. It has these weird loops. So if I go past this point and it goes down, that doesn't reflect reality. I push on the gas to compress it and the pressure drops. So think about that. Would be a weird bicycle pump, right? You pump. It's you feel the resistance of the pressure because you're reducing the volume. And then you get to a point where you push and then it pulls your hand down. That's what the van der Waals equation is saying, and we know that's not realistic. When it starts doing that in this van der Waals equation, we know that that's where the condensation region is. And so Maxwell came up with this idea of picking a vapor pressure here where these areas were equal. And so that's what you did this week. If you're in the Monday lab, you've already done this. If you're in the Wednesday lab, you'll do this afternoon. You will use Excel's solver to pick a vapor pressure. And you will look at the difference between these two areas. And when those differences are zero, then you've found the vapor pressure for the Maxwell construction. And so you're solving for these vapor pressures. So let's focus on this vapor pressure equation. There's actually equations that don't use the van der Waals equation. There's experimental equations. And so let's look at those. This Clausius Clapeyron equation is an experimental fit to the data. it uses a Boltzmann distribution to account for the energy it takes to evaporate the molecules from the surface. And so it uses multiple pressure temperature points, PT points, to determine the delta H of vaporization. Okay, so in water, we have these three reference points. We have the triple point of water, and we'll see that later today. We have the boiling point of water. We'll define what that is. And we've already seen the critical point. So we could pick any one of these as our T star. And so this T star or P star would be any pair of these. And so we could take the critical point pressure and the critical temperature, and those would be our starred values. And then this T and P would be values of interest, right? If you're interested in its room temperature value, notice none of those starred values as room temperature. We have 273, 373, and 647. What's the vapor pressure of water at 298? That would be the P and the T, the non-starred pieces. So 298 would be the T, and we can solve for P at room temperature. So that's what the Clausius Clapeyron equation is useful for. This is the plot. So if we plotted, this looks like a linear equation. So this is Y, this is M, and this is X. So if we plotted R times the natural log of P over P3, we're using the triple point here, and 1 over the triple point temperature minus T on the x-axis, we get this nice linear equation. Now this is a fantastic fit. That tells you this equation is really good because it goes from 273 Kelvin down here. Let's see, I guess 1 over 273 would be no, let's see. It's hard to figure this out. So this is the triple point temperature and pressure. So this would be the 273, and this is 647 Kelvin. It fits really well across that whole range, and that's pretty impressive. Okay. So we could take that delta H of vaporization and one of these PT points to model the PVAP versus T. So here's the pressure. If we didn't do the 1 over temperature or the natural log of pressure, this is what the plot would look like. You see it's very low pressure at room temperature and the boiling temperature of water and so on. But as you raise it up to 647, you see the pressure goes up exponentially. So if we take the log of that, we get the linear fit. If we took the log and just did temperature, not 1 over temperature, we see it's a little more linear, but it's linear with 1 over temperature, not with temperature. So this is what we would see if we just did the log of pressure. But here's like from the vapor pressure table, like from the CRC, from room temperature up to the boiling point of water, we see it fits right on that line. So it's very good. And then there's other equations that could map out the vapor pressure of a fluid, and this would be the Antoine equation. And so here's the Clausius Clapeyron equation for water, and then here is the Antoine equation. So sometimes you can find the delta H of vaporization. Other times you don't find that for a substance and you need to find its vapor pressure. You might find the A, B, and C constants, the Antoine equation, the constants. And so this would be the equation for the Antoine constants. And you can see they match pretty well. So this pink one is from the Antoine equation, and the blue one is from the Clausius Clapeyron equation. Okay. So that's vapor pressure. It's definitely, there's some calculations in the homework using these equations. So definitely encourage you to become familiar with both of these ways to calculate vapor pressure. They'll be very important when we start talking about distillation, because again, what is distillation based upon? It's based upon the vapor pressures of the liquids, and whatever has the highest vapor pressure is going to come over first. That would be the thing with the lowest boiling point. So we would be able to predict separations based on vapor pressure and determine if mixtures are going to be ideal or not based on their differences in vapor pressure. So